In this video, we're going to get to know acids and bases a little more specifically. And we're going to be talking about a specific definition, the Bronsted-Lowry definition of an acid and a base. There is another competing definition called the Lewis acid and base that we are not going to touch. So if you ever see a reference to that, you can just ignore it in this class. So what is a Bronsted-Lowry acid and base? Well, an acid, in this case, an acid is going to be a proton donator. And a base is going to be a proton acceptor. Now, what do I mean by a proton? Well, in many cases of acids and bases, we have this extra little hydrogen cation. Think of hydrochloric acid, something like this. Cl, we can think of that as the minus charge, and the H we can think of as the plus charge. These will dissociate in the solution just like an ionic substance would. And the hydrogen actually ends up being only a proton. Remember, hydrogen has one proton and under normal circumstances one electron. But when it's in a cation form, it loses that electron. So all that's left is that one proton. That means this is extremely reactive and it'll get picked up very quickly by something in the solution. And so the first thing I really want to do with acids and bases is look at something called a hydrolysis reaction. A hydrolysis reaction is any reaction where we have water splitting something. Splitting up is called lysis. Hydro is water. So we're going to use H2SO4 in this case. And we're going to put that into a solution of water. Now when that happens, H2SO4, this is going to be our acid, right? It's got these two hydrogens that it could donate. And the water here, this is going to be our base because the water is going to be the thing that picks up that proton. And so we're going to have this H2SO4, this is sulfuric acid. We're going to have this deprotonate once. So it's going to lose one of its hydrogens. And that happens very quickly, very easily, and it's going to mean that this has a negative charge. That proton is going to be picked up by the water. So that water is going to become H3O+. This is the hydronium cation. And so if we look at our left side, it's clear which ones are acid and which ones are base. The H2SO4, that gave away a proton. So it's clearly a proton donator. That's clearly an acid. But what about this other side? Is the HSO4-, is that still going to be an acid? Well, the thing is, when it gets to the other side, this HSO4-, it could theoretically pick up that hydrogen again. This H3O+, if these two slammed back into each other, this HSO4 would pick that proton back up. And in that case, it would be the proton acceptor. So HSO4 would be a base. And H3O+ in that case would be an acid. And so in order to differentiate this base from this base, on the right side of the equation, we call this the conjugate. The conjugate base and the conjugate acid. So whenever we have a hydrolysis reaction, we have an acid deprotonating, giving a proton away to something else, and something else is going to pick up that proton. And then it's going to become a conjugate base, okay? You may have noticed by now that when we work with acids and bases, we're very often going to work with them in an aqueous solution, in a solution of water. The reason for that is that water is amphoteric. Amphoteric means it can act as both an acid and a base. So if I have two water molecules here, they can react, creating a hydroxide and a hydronium. In this case, this water would be our acid, and then it would become the conjugate base of the hydroxide anion, which is kind of the definition of a strong base. And this H2O, this would be our base here. It would pick up that proton, and then it would become the conjugate acid of the hydronium ion. So water being amphoteric is very important for acid-base reactions because it could lose a proton, it could gain a proton, and this actually happens all the time in water. It's constantly happening where some water molecules are being broken up into hydroxide and hydronium, but it happens very infrequently. And this hydroxide and this hydronium are able to collide again and go back to being regular water. And so we can have this reaction going in both directions. And so when we have that, we get this thing called equilibrium. And we can make a ratio of that where we have the concentrations. Whenever we write concentrations, we put the element in these brackets. That just means whatever the number of the molarity is. If we take the concentrations of these two at any given time in water, and we multiply them together, we get this very specific number, this Kw. And Kw is one of those very interesting constants. It is equal to 1e negative 14. That's 1 times 10 to the negative 14th. So when we're looking at Kw, what this really means is that when water is totally neutral, if we don't do anything with an acid or a base other than just regular water, it's going to have this equilibrium, and the concentration of both of these is going to be equal to 1e negative 7. This will come back up as we're looking at pH, but before we do that, I just want to take a look at another acid, at another hydrolysis reaction, just to make sure we're getting comfortable with it. In this one, we're going to use carbonic acid. Carbonic acid is H2CO3. When we just write out the hydrolysis reaction, what we're going to have is that carbonic acid reacting with H2O to make HCO3 minus. Remember, bicarbonate, it's the bicarbonate anion, and H3O plus. So if I wanted to model this out, if I wanted to draw this out, let's make a little beaker model. I'm going to make a nice wide one. If I draw this out like this, then this oxygen is going to reach out and grab this hydrogen. That hydrogen is going to give up its bond to this oxygen. And then we're going to get this resonance structure and this hydronium anion. Okay? So that's what it looks like to model this out. So now that we have an idea of these hydrolysis reactions, we can start looking at the actual pH scale. That pH scale represents the power. This P is supposed to represent power of that hydrogen ion, that little proton. The pH scale is a 14-point scale. It goes from 0 to 14. And there is a competing scale with that. This competing scale is the POH scale. Now, pH is a lot more common. Maybe it just had a better marketing campaign, but POH is still very useful, and we're going to need to be able to use that as well. But how do we actually use this scale? What is this scale actually representing? Well, when we have acids and bases, things can be extremely sensitive. So I could have a hydronium ion concentration in a range from 0.000001 up to 0.000001. 1 0 less. This subtle change could have huge impacts on a solution and really the organization of a lot of different organic molecules. We will see that a few times. We have a lot of interesting chemicals that will change color with the slightest change in pH. And so we don't want to have to use a scale that goes all the way from this tiny number all the way up to a 1. And these would be molar, by the way. These would be concentrations. They would be in molarity. We don't want to have a scale that looks like this. And so what we do is we take the negative log of a hydronium concentration, H3O+. And if we do that, if we take that negative log, it takes numbers like this, and it shrinks them into numbers like this. And so we're able to use the pH scale to have a more comprehensive look at how acidic something actually is. Something that has a 6 or a 7 is pretty close to neutral. Something with a 1 is extremely acidic, where something with a 14 is extremely basic. So it's going to be very related to the concentration of the acid that is in solution. And now I want to come back to that hydrolysis reaction that water goes through. Remember that Kw value. That Kw was 1e negative 14. And what that meant was that the concentration of each of these, H3O plus and OH minus, in a neutral solution of water was 1e negative 7. If I take the negative log of 1e negative 7, I get 7. So that's why 7 is going to be neutral on the pH scale, pH and pOH. But if I start to add a bunch of acid, let's say I added, let's just say, enough acid to make a 0.001 molar solution. Well, then I'm going to take the negative log of 0.001, and that's going to give me a pH of 3. So if I have a 0.001 molar solution of an acid, it's going to have a pH of 3. If I have a 0.0001 molar concentration, that's going to give me a 4. So we can see, on a logarithmic scale, what's really happening is, as I change by a factor of 10, my scale only goes up by 1. See that? And it's going to be an inverted scale because of this negative. If it wasn't, we would just end up with huge, massive numbers. So that means is that when we have a 1 molar solution of an acid, it is going to have a pH of 0. Okay? So that's the brief introduction to our pH scale. We're going to look at that more next time. But what we really wanted to get out of this video was the definition of an acid and a base, and the hydrolysis reaction and the ability to identify the conjugate acid and the conjugate base.